Perfecto. Pues, entonces voy a comenzar. First of all, thank you so much for inviting me today. It's really nice being here to give today this talk. I hope it is interesting. And during this presentation, I will be talking about a new software that we have been working on in the biocomputing unit here in the National Center for Biotechnology in Spain, which is called a Scipion Flexibility Hub, which at the end is a kind of a framework where we are integrating different solutions to analyze macromolecular flexibility from our cryo-EM data, and also try to overcome some of the problems that we have. We are trying to reconstruct 3D maps with high resolution, and we have this kind of motions going on. Okay, so before that, I would like to very briefly talk a little bit about my academic career, but it's very, very recent. I started in the Universidad Carlos III, which I did my degree on biomedical engineering. And here in Spain, this degree is focused on 3 different branches. 2 of them are more related to biology, genetic engineering, and the other one is more for devices. And the one I chose was the one of image processing, because I really wanted to work with more on physics, computers, and so on. And I thought it was an interesting branch. So I went into that one, and I really, really enjoyed biomedical imaging. And thanks to this branch of studies, I had the chance to start working on the biocomputing unit in the group of José María Carazo and Carlos Oscar Sorzano. And in that case, it was not biomedical imaging, it was cryo-EM. And I saw many of the things I learned in biomedical imaging were useful for cryo-EM. They were very, very similar, but there were things that were very, very different. For example, the noise, which was something that was not so important in biomedical imaging, in cryo-EM becomes a strong limitation. And I was very, very curious about how to work with these very challenging conditions. And that's why I decided to go into cryo-EM. After my degree on biomedical imaging, I studied on the Universidad Autónoma, here also in Spain, Madrid, and I did my master degree on condensed matter physics and biological systems. I really, really enjoy math and physics, and in my degree, there were not as many, there were many math and physics, but also a strong biology, and I wanted to move a little bit towards the world of math and physics, and that's why I decided to move away from bio and try to do something more on these lines. And I really, really enjoyed the master. It was also very nice because I had the chance to learn a little bit more about the physics of the microscope, how the cryo-EM works actually, and I really, really enjoyed it. And also during this time, I started thinking about doing my Ph.D. studies in the group of José María Carazo and Carlos Oscar Sorzano, and I started working a little bit on the world of macromolecular flexibility cryo-EM. And with all these 2 steps, I decided to go into my PhD studies, which were again done in the biocomputing unit. The biocomputing unit is developing 2 main softwares. One of them is a Scipion and the other one is XMIP. A Scipion, I will be talking about it at the end of the presentation, but it's mostly a software for integration of other software, other packages like Relion, Cryospan, and so on. And the idea is that a Scipion will handle the conversion from one software to another automatically. So the only thing a user has to worry about is filling up a form, inputs and outputs and some parameters, then click on execute, and a Scipion will do the magic behind to make it compatible with any software. And the other one is XMIP, which is actually image processing software. So it's where all our methods coming from the lab are being developed. And in that context of XMIP, I started working on this macromolecular flexibility. So all my PhD studies have been working about how to trying to overcome the limitations that were in the field some years ago, I think 2 or 3 years ago, with 3D classification, and trying to see how we can extract as much structural information as possible from our particle dataset, mostly particle dataset, but also from volumes or atomic structures. And I finished my PhD very, very recently. Last March was my defense, and I finished my studies. I was very, very happy. I really enjoyed it a lot. Now I am continuing my career being a postdoc, also in the lab of José María Carazo and Carlos Oscar. I am finishing all the different something. I think the presentation is lost. Sorry for that. Oh, I cannot share screen.
Oh, 1 second.
Okay, no worries.
Let me check. I'm sorry about the problem.
No, no worries.
Uh, mm, uh, okay.
Okay. Yeah,
Can you share now?
I think so. Let me
Okay,
check.
perfect. I'm sorry. Thank you.
No worries, no worries. It's sharing now, right?
Yes.
Okay, great. Okay, so, sorry for that. Yeah, so I finished my PhD and I am continuing doing the postdoc, finishing some works that those are the ones I will be presenting today, which are also about flexibility and how to improve also the resolution of our volumes using this flexibility information. Uh, okay. And during my PhD, I also had the chance to publish many papers, most of them as a co-author, but some of them, these 4 papers, came out as a first author. And as you can see, they are mostly on macromolecular flexibility. The first 2 ones, they are about a method I will be talking about now. It is not exactly the same method as the one that is published in the papers. It's the evolution of this method, which has to do with a new basis based on 3D Sarnicke polynomials that are able to extract the motions of protein is undergoing that is captured in our particle images in a cryo-EM dataset. Then we have this one of SAR. I will be also talking about this later on in the presentation, which is a method that is taking these molecular motions and instead of using them to get new states, is going to use them to correct for them so that this blurring that we have in our cryo-EM maps that has to do with the motions that the particles are undergoing in the images is kind of corrected, and we are able to get high resolution on these regions that look like a blob because of the motions. And then I will be talking lastly about this Scipion Flexibility Hub, which is, as I said, is an interactive framework. And the idea is to put here not only our software, but also software coming from other groups like Relion, CryoSpark, CryoDragon into a single place so that any user can use it in a easy way, simple installation, and trying to extract as much as possible from our data. Okay, so before talking about the methods, I would like to very briefly explain the problem that we are trying to solve here, which is heterogeneity analysis. And this is not something new in cryo-EM. We have been doing this for a long, long time. I think the first papers published on conformational variability were in 2004 by Source with this new method of 3D classification, which is now kind of the standard way to analyze all this variability in cryo-EM. And the idea of the method is very simple. We have large sets of images, probably in the order of 100,000 million of images. And we know that all these images are not coming from the same object, because our proteins are not static. They are continuously moving. So instead of assuming that we can reconstruct just one volume from those images, let's assume that we can actually reconstruct K objects from them. And the problem is that this K number is not something that we can determine. It's something that we have to guess. We need to give the number of classes to the program. Could be 5, could be 10. We need to try. And the idea is that the program will try to split the images into different groups. Hopefully, these groups will represent a different conformation, and then we can reconstruct with those images in each group and get our number of classes. And with this, what we are getting is something like, for example, here in this example with the SARS-CoV-2 spike. We could get, for example, the RBD in 3 down conformation or the RBD in 1 up conformation. And this is already very, very useful because we are already getting an idea of these dynamics of the protein. But I think we have 2 main limitations. The first one is that we don't really know how these classes are connected. We don't know how the protein is going from one step to another, or really the protein is following a specific path to get to that specific conformation we're interested in. And this has to do with the way we are discretizing all the variability. And also the other one is that we are discarding a lot of information because our proteins, they are not moving in an instantaneous way. And what we are doing with discrete variability is to say that the protein is going from one state to the other in an instantaneous manner. But we know that this motion should be continuous, right? And this information is discarded with this assumption of 3D classification. So I think now the field is moving towards the idea of continuous variability, trying to extract not just K classes, but as much conformational states as possible from our cryo-EM particle images. And the idea is to escape from the static pictures and go into videos, right? Trying to see how our protein is moving from one state to another in a continuous manner, or if it is following a very specific path and so on. So this is the idea. This is what we would like to solve, how to go from a stable number of classes to as much structural information as possible. Still, you may think if going to this continuous variability analysis is something useful, because we have been doing classification for a long time, and probably with classification, even if it has some limitations, is more than enough. And for that, I really like, again, this example of the SARS-CoV-2 spike. This is an experimental data set we have been working in the lab. And after analyzing it with classical methods, standard workflow pipeline cryo-EM, we managed to get, again, these two states, which are the most common ones you can find in the SARS-CoV-2 spike, which is the RBD1 up and the RBD3 down. And if we put this on a conformational landscape, what we have is just 2 points here. So let me show you now what happens when we put on top of this image the continuous conformational landscape. We can see that the picture changes a lot. It's strikingly different. Of course, there are many things going on in the transition between the up to the down, but that's something we can already guess. But even if we have a look at the classes, let's say each of the table classes, we see that the amount of structural information in here was huge. There were many different conformational changes going on. And all this is completely lost because of the assumption of 3D classification. And that's why I think it's interesting to go into this case of continuous variability, because there is a key structural information that will really help us understand better how our protein works that is completely lost because of these assumptions. And that's why I think now cryo-EM is shifting towards advanced flexibility analysis. And this is something that we can see in the huge number of publications that are coming out in the recent years from 2023 to now. There are many different methods coming out, like Sarnike 3D, CryoDragon, 3D Flex from CryoSpar, Opus DSD, CryoStar, which used to be a bioarchive. I think now is already published method. Well, many poly-EM, many different methods, and many other methods I have not listed here because I didn't have space in the slide. So really, this is a very hot topic, and the idea is, okay, we have software, but how can we use the software, and also in which cases should we use one software or should we use another program? This is what I would like to discuss in this presentation. So actually, depending on how we are estimating this viability information, we'll split the software into two different types of programs. And these are not official names, but I really like them, and I think some other people are also using them, which is that we can split this method into what we call the density-based approximation and the deformation field-based approximation. And the idea at the end is the same. We want to estimate the structural states, but the approach they are going to follow is slightly different, and this means that the information we can estimate will also change a little bit. So I'm going to start with the first one, which I think is the most simplest one, which is the density-based approximation. And actually, density-based is just a funny name to say reconstruction. If I want to get a state A and a state B of my protein, well, one simple way to solve the problem is let's get the images belonging to a state A, let's get the images belonging to a state B, and let's do a reconstruction with those, and in principle, the problem is solved. I already have my two states, which is the information I want to estimate. So as you can see, this is the same as what we are doing in a 3D classification, which could be also categorized as a density-based approximation, right? Because at the end, we have some data set of images. We are splitting them in a clever manner. We are then reconstructing with these images different states. And hopefully, these states will represent the conformational variability of our protein. And I am not going to repeat this, but as we said, there is a problem with classification because it's introducing many assumptions, and this at the end reflect into several limitations. So the problem here is that we are doing this part here. We are doing what we are calling a homogeneous reconstruction. That is, from many images, I get one volume. And here is where the problem is lying. Because really, if one particle is representing a virtually different conformation of my protein, as soon as I am starting to average different images, no matter how small the number of images is, I am mixing up conformations. So we would like to escape from this case here, which is the case of standard reconstruction of 3D classification. And we would like to go to this new problem here, which is the heterogeneous reconstruction, which ideally means if I have one image, then I want to reconstruct one volume from one image. And of course, this problem is impossible, cannot be solved. Even if the images were completely ideal, with no noise, no CTF, we remove all the artifacts and we have a completely clean image, this problem is impossible to solve. You cannot reconstruct an object from just one projection. But actually, using deep learning tools, we can give a very nice and accurate approximation to this same problem here. And that's why there are many, all the methods that are coming out following this approximation, like CryoDragon, like Opus DSD, and so on, they are relying at the end on deep learning to solve this problem. And of course, we also wanted to work on this problem and trying to give it a solution. And we came out with a new method called Hetsiren, which is, again, a deep learning-based method because it's the most accurate way to solve this heterogeneous reconstruction problem. As I will show you later on the slides, it's not only solving the problem of reconstruction, but also the problem of refinement. Because I think at the end, we already have structural information that is coming out from our workflows. Then why don't use this information also to train these networks and to improve a little bit all these conformational variability estimations? And at the end, Hetsiren works in the way this described here in this scheme. I will go, I will leave a brief summary of how it works. So at the end, Hetsiren is based on an architecture in deep learning, which is very, very common, which is called an autoencoder. The idea of an autoencoder is actually very, very simple. The idea is that we have some input. In this case, are going to be images, could be any other input. Then we have our neural network, which at the end is a black box. We don't know what the network is going to do. But what is important is what the network is going to get out of the last part of the network, which is the decoder, which at the end is going to be also images. It's going to be the same, something that is as similar as possible to the input. So actually, the network is going to learn to codify and decodify the input to produce an output that is as similar as possible to the input. And then we can compare the output and the input and train our network. Of course, having an output that is exactly the same as the input wouldn't be useful. It could be useful for some other applications, but not for this one. But we can try to modify the network to get an output that is keeping some properties of the input, but is also trying to improve some other characteristics that we are interested in. So how are we doing this in Hetsiren? So in Hetsiren, we are starting always with our experimental particle images. These images already have alignment estimated, CTF estimated. And the idea is that these images will go through this encoder. As I said, encoder here is deep learning based. It's a black box. We don't know what is going on inside the decoder. The only thing we know is what is coming out from the encoder, which are three bottlenecks. Basically, we are going from the image space to a reduced dimensionality space. The first two spaces are basically a matrix, alignment matrix refinements. At the same time, we are finding a new conformation. We might want to refine a little bit the angle and the pose of our particle so it matches better the underlying object. And then the other one, this set here, is going to be at the end our conformational landscape. So this one will have an organization of the images in the shape of a point cloud that is organizing them based on the conformation they have captured. So at the end, this will represent the conformational landscape. So from here, from this conformational latent space, we are going to input it into a volume decoder, which is going to go from this reduced space to a whole volume in real space. So if our volume is 300 voxels box, we have 300 to the cube voxels here, and we can recover the whole volume. Actually, this volume is not just a volume. It's what we are calling a refinement. It's a delta volume. So this delta volume can be added to another prior volume, which is optional. I will show you later on why this volume could be optional or not. And once this volume is added to a prior volume, we are getting our final reconstruction. And then this reconstruction is projected. We are getting with this projection, a theoretical projection of the volume. The projection is CTF corrupted. Then these are the images that we can compare to the input. This is the output of our decoder. And then if we compare the output images with the experimental ones, we can establish a cost function and we can train our neural network. So this is, in essence, how a Hetsiren neural network works. So if we go to a very, very schematic view of Hetsiren, this is how it looks like, actually. It's just, as I said, an autoencoder. We have images coming into an encoder. We are generating some bottlenecks, and we have a decoder that is going from these bottlenecks to an image. And of course, some mid step is to produce a volume. That is the one that we are interested in. If we just do this, then the network might not learn what we are interested in. We should define what we are interested in. What we want is to have, of course, a conformational landscape, something that is representing all this organization of the images based on their conformation. But also, we would like to have good quality on the volumes that we are decoding. We don't want to have just a volume that is more or less representing the conformation. We would like to see features. We would like to see really all these high resolution structural features that will allow us to understand how or what these conformational changes are doing. And also, we would like to use structural information as a prior. So I think most methods will discard most of the information that we are having in our workflows of cryo-EM, but this information is useful, and we should try to find ways to recover it and to use it in this kind of neural networks. Actually, the part that is most interesting is the decoder. And as I showed you in the scheme, the decoder can be divided into two different parts. One is the map decoder, which is the one taking this conformational space and is going to produce volumes from it. And then we have the physics decoder, which is the one doing the projection, doing the CTF corruption of the images and so on. So this one is not so interesting, because at the end it's based on our knowledge. We know how to project a volume, we know how to apply a CTF. So this is not something very, very interesting. I think the one that is most interesting is the map decoder, because this one will really determine the quality of the volumes that we can get. So how does this decoder works? Actually, anything that we express in deep learning, it can be written as a function. So basically, any decoder layer in deep learning is a function that is taking some input and is producing an output. In our case, we have a function that is taking this conformational latent space, and it's going to produce at the end this delta volume. So this is what the decoder is doing. It's a mapping. And then this function here, usually in deep learning, is multiplied by some other function, which we are calling activation. And the idea is that this function that we are multiplying will change a little bit the behavior of the network, will make it learn better. And there are many different ways to activate a function. And one of them is called sirens. These siren layers is an activation function, which at the end is a sine and a cosine. So we are multiplying every single function here in the decoder by a sine and a cosine function. And this may seem very silly, but actually has a strong meaning in deep learning. And I really like this image. It's taken from the paper that first introduced the concept of siren layers, these sine and cosines in deep learning. And they were comparing a very similar task to the one that we are trying to solve in cryo-EM, which is reconstructing an image, but with a neural network. So they were taking this very famous cameraman image, and they were taking some of the derivatives, the first derivative and the second derivative of the image, which has a lot to do with the features, the quality, and so on. And then they were comparing the performance of a network when different activation functions were put into that one. And as you can see, many of these functions do not work very nicely. The image that is coming out is not so good. Two of them are performing much, much better, which is this ReLU-PE. In fact, this one is the one used by CryoDragon. So this is already being used in cryo-EM. And then this siren one here. As you can see, at the level of the image is quite similar. The quality is quite good. First derivative look good in both cases. If we could zoom in this here, siren will be a bit better, but the difference will be that much. But then in the second derivative, you can see that really ReLU is not performing well, but siren is doing a very, very good job, which means that siren is reproducing not only the image, but also features of the image, like the curvature in the image, the features, structural features in the image, and so on. And that's why we wanted to use these siren activations in head siren instead of the ReLU-PE ones. So this will modify the quality of the volumes that we can get, because this will help the network learn volumes with high resolution. And then with this, we can produce our delta volume, which, as I told you before, is a kind of a refinement. And depending on what we are refining, we can train the network in two different modes. So let's suppose the volume that we are refining is a volume full of zeros. Then if I add this delta volume, the delta volume is the same as the volume. So this is a reconstruction. The network is learning how to produce and complete volume from scratch. But if we are giving it some initial volume, like for example, a volume coming from a 3D classification, a refinement, or something like that, and we adapt this volume, then what we are doing is to further refine that volume towards a new conformation. So the network is working in refinement mode. Thanks to this, we can modify or customize the training based on our needs. If we already have this information available, we can put it into the network. If we want the network to learn something from scratch, we can do reconstruction like in CryoDragon or any other method of deep learning that is also doing this variability analysis. Okay, so we know how Hetsiren works. We know what it's trying to do. It's a 3D reconstruction from images and also this organization of the conformational latent space. So actually, how can we use it? And I will be talking about how we can use these things on a Scipion later on, but just as a kind of a spoiler of those slides at the very end, the Scipion at the end is working with a workflow architecture. So you have a graphical interface. You have an interface where you have basically a workflow. A workflow is just a box that is connected to some other boxes. And this box will represent a software. Could be a refinement in Cryospark, could be a movie alignment, could be motion core, any software you may think of. And this box, if you double click on it, it will open a form. And this form has some parameters of the program that you are going to run. You can fill the parameters, click on execute, and Scipion will modify the inputs and so on, so the program can run. And the same idea goes into flexibility analysis. At the end, what you will have is a box, which is this flexible aligned head. This is the training of the network. So if you double click on it, you will have some parameters that you will need to fill up. Most of them will be set to some default value, and this will be working fine. And if you execute this, you will be training the network that we saw previously. This network will produce a very important piece of information, which are these conformational latent space here. So this information will be recorded into Scipion. And this conformational latent space has 10 or 8 dimensions. So it's something that we cannot see because it's a high dimensional space. So you can go into a different box, a different protocol, which is a dimensionality reduction, which basically will take the output of a head and it will reduce it to 3 dimensions, to something that we can see, that we can interpret. And then this will go into a tool that we have also been working on, which is an interactive tool to view your conformational landscape. And then once you have deep visualization of the conformational landscape, you can click any point here, even you can drag the mouse, and you will be seeing here your volume updating automatically based on what the network has learned. So basically, you can draw a path, you can select different regions, and you can see in real time the conformational change that is going on. And you can see that this is very, very powerful, right? Because this landscape is coming from all the images in your data set. Every single point here that you click here will correspond to an image, and you can extract that information in real time and get the confirmation of that specific particle in real time in 3D with high resolution, hopefully. So this is the way we are working with Hetzire in the Scipion. And actually, we always need to compare to others to see how we are performing. And yeah, here the one that is always suffering the comparisons is CryoDragon, because this is the first method that came out doing this deep learning reconstruction of many, many states from particle images. So it has become kind of the standard, and that's why we need to compare to it and see how we are performing. So we decided to take a very well-known dataset, which is this Empire 1028. It's a ribosome dataset. It is being used by all methods to determine if they are working fine or not. And we took this dataset, we ran Hetzire and CryoDragon, and these are the conformational landscapes that are coming from the two methods. The first thing we can see from these conformational landscapes is that the main point cloud is very similar in both cases. We are getting a main conformational region with 2 other regions coming out, and this will represent different conformational changes of the ribosome, like a rotation of the small subunit and so on. But if, for example, if we click a point here, I try to click here the same point in the landscape. It's very, very hard to get an idea. You can see that this is the volume that the network of CryoDragon is giving you, and this is the volume that the Hetzire network is reconstructing. And as you can see, the resolution is not the same. And this has to do with this special focus that we are paying on the quality of the volumes that are coming from the network. So really, you can analyze things with a very, very high resolution with Hetzire. And the other thing that you can see is there is another region here that is not present in CryoDragon, which is actually represented by a very few number of particles. I think it was around 600 particles, so really something that we cannot reconstruct. And if we ask the network to give us a volume from this region, this is what we are getting. So it's a very, very strong compositional state of the ribosome, which is losing the small subunit. And of course, this was very, very low represented because it might be a denaturation or assembly process of the ribosome, which is not present in this data set. But still, we were able to see it with Hetzire. And as you can see, the resolution is quite good, even if it is coming from a very, very low number of particles. And again, we are paying out of focus on resolution in Hetzire. And here you have a nice comparison of this same dataset, a volume coming from the main workflow in a Scipion. So it's a standard workflow doing refinement, classification, and trying to get high resolution from a set of 50,000 particles. And this is the volume that is coming out from non-uniform refinement in Cryospark. This is one of the volumes that you can get from the conformational landscape in Hetzire. And here are the resolution histograms of these 2 volumes. And as you can see, Hetzire is doing a very, very strong push of the resolution toward the high frequency regime. So this means that you can get not only nice reconstruction, but also nice reconstruction for many different points in the landscape and understand much better what is going on with your conformational changes. Okay, so this is what I wanted to talk about, the density-based approximation. So at the end is reconstruction of states in a funny way, using deep learning, but it's reconstruction at the end. So what is this deformation field-based approximation doing then? Well, as I said, at the end, both a deformation field-based and a density-based method will estimate the same thing. We want to get states. We want to get state A and state B based on our experimental particle images. But here, instead of reconstructing, we are going to do something a bit different. So for that, let's suppose that we have this Eiffel Tower image. We can have two states of the Eiffel Tower, the wavy Eiffel Tower and the, say, standard or straight Eiffel Tower. And let's pick one as a reference. Let's pick this one as a reference. Is there a way to move the pixels in this image so that when I move them, I get the second image? Actually, there is, and it's something that we can estimate. And this estimation is actually going to estimate the motion, right? The motion that we need to apply to one image to get a second image. In the context of proteins, this makes even more sense because what we are saying is if we have a reference volume and we apply a motion to it, then what we are applying is the motion that the protein is suffering to get to a new conformational state. And this is what we are doing in the deformation field-based approximation. We are going to estimate the motion, and if we know the motion, we can recover the state that we are interested in. Of course, motion needs to be expressed in some way, and the easiest way to express it is as a vector field. For each point in my protein, I can find a vector, which is going to move that point to a new position. And if I gather all the points, I will have at the end this deformation field. So we want to estimate the motion field, the deformation field that we need to apply to a reference volume to get to a new conformation, that is the one defined by experimental particle images. The problem is that deformation fields have a huge number of parameters. We are talking about millions of parameters, so we cannot really estimate that for a complete set of particle images. So instead of that, we need to find a way to reduce the number of values that we need to estimate. And one way to do that is using a mathematical basis. A mathematical basis is something similar to what is a Fourier transform at the end. A Fourier transform is going from a space, which is real space, is taking it to a new space, which is, for example, the Fourier space. And in that space, we have some coefficients. In the case of Fourier, it will determine the frequency and so on, as we all know. And one thing that we can do is what happens if I take a few number of coefficients to reconstruct or to recover my original image? Well, depending on the coefficients we are taking, we are getting the same image as the original one, but with different characteristics. For example, if I remove the high frequencies, I will be recovering just a blur image of my protein. So here, in this problem of estimating a motion field, we are going to do something very similar. We are going to take a new basis, which is called the Zernike 3D basis, which is composed by some functions. These are the functions that we are working on, which are this set. It's a composition of spherical harmonics and Zernike polynomials. And then we will have some coefficients similar to the Fourier transform. And these coefficients will also express the importance of every single component of the basis in the composition of the whole motion. If we want to have a very, very accurate definition of the initial motion, we need a very, very large number of coefficients and basis components, very similar to the Fourier transform. We need a huge number of frequencies. But what if I truncate the number of frequencies to a small number? Then here we can just have a very few number of coefficients in the order of hundreds of thousands, and we are recovering a motion which is not exactly the same as the original one, but is, well, probably reproducing in an accurate way the motion, or is probably more low resolution motion, but it could be more than enough to recover the conformational change that we are interested in. So this is the problem that we are trying to solve. So we are going to use this basis to estimate a set of coefficients. From the coefficient, we can recover the vector field. And from the vector field, we can apply it to a volume and get a new conformational state. And actually, one thing that this Zernike 3D basis has is that it's very, very versatile, because actually a motion can be applied to many things. For example, we can apply it to a volume, right? As we said, we can take two volumes and we can estimate the motion between these two volumes, and we can recover the conformational change between them. So we can apply this basis to the volume case. But we can also apply it to the case of particles. We could, for example, take a volume. We could apply a motion to the volume, project the volume, and compare our experimental image with the image that we have moved, that we have projected and moved. And in that way, we can also try to approximate the motion based on the information of a particle. So it can work also with the particle datasets. Even it can work with the structural models, because at the end, what we are just doing is to move an atom to a new position. So it is even simpler in the case of a volume. We are just taking it to a new coordinate position. So actually, this means that this method, we can work with any kind of data type in CryoGen that we want. And this will have a nice implication in the method, as I will show you later on. Problem is that this Sernike 3D program was a classical program. It was working nicely. It has some limitations, but we have managed to overcome them with the evolution of the method, which is called Sernike 3D. So again, taking the method to the deep learning world. But as you will see, this is a bit different compared to Hetsiren. I would like to call this kind of network semi-classical, because actually they are not completely deep learning networks. They have a part of that is deep learning and a part that is kind of our knowledge, is physics-based, let's say. So how does the network, this neural network works? As you can see, the first part is very similar to Hetsiren. We have experimental images. This is the information that we have, is the ones that have the conformational information. These images will go again through an encoder. This is the part that is deep learning in this network. We don't know what is going on in this encoder. The only thing we know is that three things are going to come out. The first two bottlenecks, again, is an refinement of the pose of the particles. So it's the same thing as in Hetsiren. We are going to refine the pose as we are finding new conformations. But then here we are getting something different. In the case of Hetsiren was this set, this conformational latent space. In the case of Sernike 3D, these are the Sernike 3D coefficients, the ones that we can use in conjunction with the basis components to recover a deformation field. So in fact, this part here is not really deep learning, is math-based, right? Because this should have a mathematical meaning. And in fact, if we combine these coefficients with the basis, we should be able to recover a motion field. And if I have a reference volume, for example, I could apply the motion to the reference volume and I should get a new conformation. So this is the idea. This part here is not deep learning based, it's based on our knowledge on how to use the Sernike 3D basis. And once we have the new conformation, we can again project it. Once we have the projection, we can apply a CTF correction. And with this, we have an image that we can compare to the experimental one, and we can train the network. So here, if we compare to Hetsiren, the network we were seeing before, all this part here will be the decoder plus the physics decoder that we were seeing. But here we don't have a volume decoder. Here we have a physics decoder that includes the knowledge on how to project images and the knowledge on how to produce motion fields from Sernike coefficients. So this physics decoder is not learning anything. It's based on our knowledge, and we are giving this knowledge to the network, and the network will learn how to use it to produce a meaningful Sernike coefficients. So this is the idea. But again, as I said, this basis can work with different types of data. And we were saying we can give a reference volume to the network, and we can apply a motion to this volume. We can project it, and we can use it to compare to the images. But what if we have also an atomic model that we have traced in our reference volume? Then we could also apply the motion to that one, right? Because at the end, we can just take the Sernike coefficients, we can span a motion for those atoms in my atomic model, and I can apply the same motion to the model and to the volume at the same time inside the neural network. And then this opens a very nice possibility, which is let's use the volume to compare against the particles. Because at the end, the volume is coming from the images. So this seems very, very consistent. But then let's use the atomic model that we are moving to evaluate some stereochemical constraints. For example, atoms should not clash, or the bonds should have some distance. We cannot have bonds that are very, very short, bonds that are very, very long, or even the dihedral angles in our proteins should be conserved. This basically means that motions in a protein are restricted. We know that the motions has a lot to do with physics, with biology, and we cannot apply just any motion field to them. They should respect the geometry of a protein. And the idea of this is that we can apply this Sernike basis at the same time to a volume and to a model to get not only motions that are compatible with experimental information, but also compatible with what a protein looks like. And this is a very, very unique property of this method. There are other methods also working with atomic models, but there is no method that is working with this information at the same time. And I think this is very, very powerful and is giving a very nice way to customize and learn much better things from this kind of neural networks. So again, how this Sernike 3D works? Well, it's very similar to Hetsiren, because at the end, for a point of view of a Scipion, you will have your Scipion box, which is in this case flexible aligned Sernike 3D. Here there is a typo; it should be deep. And this will produce a form for you. You will fill in the form parameters, and if you click on execute, you will be training the network. Again, this network will produce a very important piece of information, which are the Sarnicki coefficients that are going to be saved. And then again, these coefficients will have still a high dimensional, they will live in a dimensional space. Will coefficients, it depends on how accurate you want to be. As we said, can truncate the coefficients in, well, depending on the accuracy that we want to get. Then we can apply a dimensionality reduction to these coefficients so we can visualize them. And again, they can be put into the tools that we have developed for seeing the landscapes. And you can do something very similar to Hetzinen. You can see the landscape, click any point in there, apply the motions automatically in real time, and see how your protein is moving, depending on the region of the conformational landscape that you are. You can start understanding what is going on with all these different motions. So what we have been doing up to now in this Sarnicki 3D method is something we could call landscape exploration. Basically, as we said, we have reference volume. We have estimated a conformational landscape that is coming from the Sarnicki coefficients. And we can click on any point here, find the motion, apply the motion to the reference volume, again, get a new conformation. And this is what we have been doing. But motions actually are vectors. So if I know how to go from A to B, then I should also know how to go from B to A. So this means that instead of going from the reference to a point in the landscape, I could go the other way around. I could go from any point in the landscape to the reference volume. So the idea is something like this here in this draw. So basically what we are doing is to collapse the conformational landscape to a region that is close by the reference state. And this idea looks very, very stupid, right? Because actually we have estimated information and we are discarding it. So why do we want to do this? Well, of course, if we want to explore conformations, this doesn't make any sense. But what if we are talking about reconstruction? Well, if we are talking about reconstruction, things become very, very interesting. Why are we getting blurring artifacts in our cryo-EM volumes? Due to many, many different things. But one of them is the motion of the proteins. Because at the end, when we are reconstructing, we are kind of averaging images. And because the images do not have exactly the same conformation, this means that there are regions that are moving a lot, and these regions that are moving a lot will be averaging into a blob, or they will be lost completely. And this is very exaggerated. This is not real. It's what could happen if a protein is moving a lot, right? We have some protein, it has some landscape. We are taking all the images. We are doing a homogeneous reconstruction with any software that we like, and we are getting this volume here. Regions that are not moving will look very nice. They have high resolution, but regions that are moving a lot will have very strong blurring. So what if we can, as we said before, collapse the landscape to just one point? Well, if we can collapse the landscape, then it means that all the particles will have exactly the same conformation. So if we reconstruct a homogeneous reconstruction, we are recovering again the region that was not moving, also the region that was moving a lot. And in principle, we should be able to get as high resolution as in the one that we have here, in theory. Of course, things will not be as ideal as in this case, but it should be possible to do it, right? So can we do this with the Sarnicki motions that we have estimated with the Sarnicki 3D network? Actually, we can do it. And the idea is to use these motions as a non-linear alignment. And then if we are aligning the particles based on these motions, we can try to improve the resolution of our volumes. And for that, we have been working on a new method, which is called SART, which is based on an ART reconstruction method. It's a very well-known method in cryo-electron tomography. It's real space reconstruction, and it's nice because it allows to introduce a priori information very easily compared to Fourier reconstruction. So that's why we decided to go into this method. And the idea is that this method will take into account many different things, but one of them will be the motions we have computed with the Sarnicki 3D basis. We will be able to use them to improve the resolution of our volumes. One example, what happens if we compare a cryospan reconstruction, again, of this ribosome, this Empire 10,028 dataset, with SART when we are applying these motions? Well, you can see that things really change a lot. Really, when we are comparing the two volumes, we see that this one is not looking as blurry as this one. And even in the region that it was moving a lot, we start seeing some features here where we're not possible to see them. And this has to do with this motion correction, right? Of course, depending on the case, things will work better, things will not work as good. It will also depend on the degree of motion. But as you can see, things can improve quite a lot. What happens if we compare, for example, SART with just reconstruction, no flexibility correction, which has a similar performance to cryospan reconstruction or reliant reconstruction with the motion correction of SART? you can see that really the map, even in 3D, is changing a lot. You can see now, for example, these RNAs here, they are looking much better, and we are able to see much better the structure of the RNAs. Or for example, here in these alpha helixes, now we are able to extract much better all the side chains. And this only has to do with the correction of the motion of the alpha helix in the ribosome. And again,
I'm sorry,
yeah.
Dr. David, you have 5 minutes, please. Thank you.
Okay, yeah. Okay, thank you. Yeah, I will finish fast. Yeah, thank you so much. So, so basically, we can do this. For which point can we do this motion correction? So in principle, we can do it just for the reference volume, but in a Scipion and in the CERN3D method, we have also worked in a way to reassign the motions so that you can apply this motion correction to any point in the landscape that you are interested in. So you can virtually correct the motion of any point on the landscape. And again, there are cases where this method does not work. And when it's not working, when the motion is so big that you basically have a region that is looking like a blob, and you are aligning a blob towards the images. Of course, you cannot expect to get suddenly a secondary structure if you are just starting from a region that is looking like a blob. But luckily, if things are not working on the first time, one thing that you can do is to make the process iterative. And you are entering in a process of estimating the motions of the protein and correcting for the motions and progressively trying to improve a little bit the resolution of your volumes until you are getting something that is much more meaningful. And this is something that we are calling flexible refinement. And we have tested it in many different cases. One of the ones I like the most is one we did in collaboration with Professor David Zagar from UCSF. And he had a very challenging protein, which was this HSP90 protein. It had a region that was moving a lot. But here you cannot even see it because of the threshold in Chimera. It was looking like a blob. And if I put the threshold very high, the region is lost. And you can see the comparison here with flexible refinement. You can see that the region is not only recovered, but even from the blob, from nothing, let's say, we are able to recover even secondary structure. So really, you can expect to get high, or let's say high resolution or higher resolution than the one you had when you were starting with the initial volume. And of course, in a reconstruction, you have a static picture, but in flexible refinement, you still have the dynamic information of the protein. So you can still see at high resolution what your protein is doing, how all the different regions are moving. So with this, I finish on the methods that we are working on in the lab. And oh, sorry for this. But I would like to, oh, okay, let me go back. I would like to finish very fast talking about the Scipion Flexibility Hub, because I think it's not only about developing methods, but actually is trying to make the ethos easy to use, to simplify the installation, to simplify the usage. And for that, I really like Scipion, because as I was telling you, it has this nice interface. You can define workflows. It will handle the conversion between different softwares automatically. And then if we have so many softwares in continuous variability, then why not also doing this for conformational variability programs? And that's why we have been working also on this Scipion Flexibility Hub. Basically a place where we are integrating many different tools, our tools, Cernic3D, HedSiren, but also tools from other groups, Dragon, 3D Flex, and many other tools, in such a way that you can run one or the other, install them in an easy way, even combine them in many different ways, and also giving you tools to interact with the results, like this tool for exploring the landscapes in real time that I have shown you during the presentation, even tools to do consensus, to compare how robust the output of two different softwares or even the same software is when running them independently on the same data and so on. So how does this work? Well, this is how a Scipion is structured. So basically a Scipion is giving you an interface. As I said, you have different boxes. Each box is a program. A program could be just a program to import data, could be a program to reconstruct with CRISPR, motion core, 3D refinement with rely on any program you may think of. And in the case of the Flexibility Hub, you have here the programs of flexibility. The Cernic 3D one that we talked about before, HedSiren, CryoDragon, you have consensus programs. And as you can see, once you are attaching these boxes one after another, you are defining a workflow. So it's very simple also to reproduce all this workflow and to share it with a colleague or try to see what you were doing some days before and try to do something different and so on. Also, we are working again on tools to analyze your data, not only estimating complex conformational landscape, but giving you ways to explore the landscape, extract different regions and understand the motions and the conformational changes that are happening in your data. And of course, many other things, like for example, advanced way to visualize the motions, like with this kind of arrow plot where you can see which regions are moving the most and towards where they are moving, or even tools to go from volumes to atomic structures and trying to see all these conformational changes at the level of atoms. All these tools are implemented into Scipion, and you can combine them in any way you want. And of course, this software is released, and in fact, I did a release very, very recently with a lot of improvements on the installation and so on. So if you want to install it, it's available, it's free, and we are always very happy to help you install it on your workstations or on your machines. And just to finish, I would like to thank the biocomputing unit in the National Center for Biotechnology here in Spain, because they gave me the chance to work with this very interesting topic of flexibility during my PhD studies, now during my postdoctoral career. And of course, without them, it wouldn't have been possible to develop all these new things. And that's all. Thank you so much for your attention. And if you have any questions, I will be very happy to answer them.
Hi, David. Excellent presentation.
Thank you so much.
Well, I have a question about, okay, this is a workflow to work with a single particle with
Yes.
different regions, but if I want to work with a encapsulating with a charged protein, this protein have a different orientations and don't have a good resolution in the 3D model. What pathway I need to solve this problem?
Okay, so I think, well, it will depend on the software, but most tools will work always with the same kind of data. So most of the programs will need a set of particles, and these particles, of course, SPA particles. There are also programs for tomography, but we don't have them yet inside the Scipion, so we are always talking about SPA. And the only thing that you need is that these particles have angular alignment information already estimated for them, and also CTF. CTF, I think, is in some cases, some programs will be mandatory. In some other programs, if you have corrected for it or you have a specific case, you might not need to have the CTF information. But in principle, it's also a mandatory parameter for many softwares. So if you have that, you can, in principle, train your neural network. Of course, depending on how good that information is, the result of the network will vary a lot. Let's suppose that you have angular assignation that is giving you a volume of, I don't know, 6 angstroms. Of course, these neural networks will try to correct the alignment. They will try to improve the resolution by estimating different conformational changes. And you might expect a slight improvement on your resolution of your maps. But you will not expect to go into high resolution. Still, if the conformational change is big enough, you might be able to see it at a resolution of 5 angstrom. So it wouldn't be a problem. Still, I think even if you have low resolution data, it's quite interesting to try these tools, because probably your low resolution is coming because you have strong motions. And this program will allow you to filter out those strong motions. So if you have a way to split your data set in this conformational landscape, you can now, for example, select a region that is just having a very specific conformation, or where the conformational change is more limited. And then if you refine that region, even with classical methods, you will get a high resolution from that data, because you are basically removing all the other conformations that were preventing you from getting high resolution. So I don't think it's a problem of, I think the starting point is quite relaxed. It really depends on the kind of information you want to estimate, or how high resolution you want to get.
Okay, since I understand that I need to choose the specific restraints to my structure. Well, I think in dissolve to a solution for my problem, to apply a restraint with another protein in Scipion, and restrain the lot of movement to a charge.
So in principle, the degree of motion shouldn't be a problem. So even if your protein is moving a lot, this program should be able to find it. So you don't need to start from a very restricted data set. In fact, I think the way many people recommend using these tools is starting from even the particles coming out from the initial volume. Of course, the network will not learn to produce very good maps from that. But this is probably a better way to clean than 3D classification, because you are basically cleaning in the continuum space. You are not cleaning in the discrete space of the classification. So in principle, the degree of flexibility shouldn't matter. Of course, this is not completely true. It depends on the method. Density-based approximations, it doesn't really matter the degree of flexibility that you have. They will work fine. For the formation field-based ones, you will need to add some regularization to the neural networks to work with very high or very movable regions. This will depend on the program. Like for example, 3D, we have some parameters, some regularization factors that you can put in the form. It's just a number. The bigger the number, the more restricted you are. In the case of programs like 3D Flex, for example, they have a mesh and they are defining a mesh in the volume, and you can touch how the mesh is defined, and they are regularizing based on that one. But in principle, it shouldn't matter if your protein is moving a lot. You can play with all this in the neural networks.